Thank you for your introduction. I'm Shun Muramatsu from the University of Tokyo, Japan. I'd like to talk about this title. Recently, cardiovascular disease, CVDs, are the leading cause of death. And it accounted for the 32% of global cause of death in 2019. There are various indicators that can help the early detection of the CVDs. And SI is one of the important information indicating some CVDs. SI is explained below. The black waveform is heart sound, consisting of the first heart sound S1 and the second heart sound S2. The S2 actually consists of the two components, A2 and P2. The interval between the A2 and P2 is known as splitting interval SI. However, it is difficult to calculate SI from S2 signal. For example, the left S2 consists of A2 and P2 with SI of 0 milliseconds, and this S2 appears to be a single sound. On the other hand, the right S2 consists of A2 and P2 with SI of 30 milliseconds. However, this S2 appears to be a single component, like left S2. So it is difficult to calculate the SI from these S2 signals. So this study aims to develop an SI estimation algorithm requiring only microphones. It can realize the early detection of some CVDs in resource-poor settings, for example, using a smartphone like this figure. And this is the overview of our SI estimation algorithm. This algorithm separates A2 and P2 from S2 using two ideas, the mixing vector and S model. Before explaining overall of the algorithm, I'd like to explain the two ideas. First, about the mixing vector. S2s are considered to be measured with 2 microphones on the chest wall as follows. The two sources of A2 and P2 are the closure sound of each heart valve. These sounds are mixed by mixing matrix and then measured on the 2 microphones as S2. So, as long as the demixing matrix, which is the inverse of mixing matrix, can be found, the true sources can be reproduced. The demixing vector W is one law of the demixing matrix. So what I want to say here is appropriate demixing vector W can separate A2 and P2 from S2. Next, about the S2 model. We modeled human S2 expanding the reported fixed valvular sound model. The detailed explanation of this equation is omitted, but this model has parameters to absorb individual differences, including occurrence timing, durations, and characteristic frequencies. In other words, appropriate parameters theta can express human S2 as a time signal. And once again, this is the overview of our algorithm. Our algorithm complementarily search for appropriate W and theta. Specifically, W and theta are optimized, simultaneously optimized to minimize the error of between the output and S model as a loss function. This process can be can be find appropriate W and theta and can separate A2 and P2 from S2. And then the SI can be calculated with these separated A2 and P2. We evaluated our algorithm by simulation and experiment. In the simulation, a dataset consists of S2s simulated with various SIs, as in the examples below. SI of this dataset is estimated by our algorithm, and error between estimated and true SI was evaluated. It is simulation. And in the experiment, the dataset consists of recorded human S2s, like the figure. The heart sounds are measured by 2 microphones on the human chest wall, and S2s are clipped for dataset. SI of this dataset is estimated by our algorithm, and the consistency with reported physiological features of the heart was evaluated. It is a simulation result. SI could be determined with an error of 0.63 plus or minus 0.62 milliseconds. The left figure shows the relation between true SI and the estimated SI. It indicates that our algorithm could be calculated the simulated SI with a coefficient of determination R squared value of 0.996. The right figure shows the relation between true SI and the difference between estimated SI and true SI. It indicates the mean of error is 0.63 milliseconds, and the standard deviation of error is 0.62 milliseconds. In the experiment, A2 and P2 were separated from the recorded human S2. The rest waves recorded S2 on the 2 microphones. These waveforms are different due to the different measurement position. In the center plot, red dashed line is the optimized S2 model. And blue solid line is output S2 by optimize the demixing vector. And in the right plot, the red dashed line is optimized A2 model and P2 model, and blue line is actual separated A2 and P2. Then SI is calculated with this A2 and P2. As a result, calculated SI is consistent with reported physiological features of the heart. But is S2-S2 interval, which indicates the respiratory phase. Specifically, low S2-S2 interval indicates inhalation, and high S2-S2 interval indicates exhalation. On the other hand, it is reported that SI increase on inhalation and decrease exhalation. The SI estimated by our algorithm, plotted as red line, is consistent with the reported features, and it indicates our algorithm successfully calculated the human SI. This is conclusion. In this study, SI estimation requiring only microphones was developed. It could determine simulated S2 to SI with an error of 0.63 plus minus 0.62 milliseconds. It could determine recorded human S2 to SI being consistent with of the hertz. It is effective in resource processing because it only requires a device with built-in microphones, for example, a smartphone. That's all. Thank you.
Thank you very much.